All right, back to regularly scheduled programming. So quiz 3 is set. It has a scheduling question, which is fairly short. That's a multiple choice. 10 general multiple choices on virtual memory. Then kind of written response about scheduling. Then page replacement, which is like page faults. So it'd be like optimal, least recently used, or FIFO that you have to worry about for that. And then there's a paging question. You can expect multi-level page tables. So with that, we will switch topic to the last kind of thread of the course and talking about persistence. And first we'll talk about hardware and maybe older hardware that some of you might not have seen. Good old hard disk drives. So this is the actual hardware of the hard disk drive and kind of what it looks like if you tore open one of the like spinning rust hard drives. It looks something like this, where there's a bunch of platters. So each of those big spinning disks is called a platter, and that's where all your information is stored. So it's all magnetic, so it's read as a 1 or a 0, so that big arm assembly there has multiple arms, and at the head there, it can read whatever, it can do some magic with magnets and actually read or write bits to the disk there. So then when you talk about the disks there, so each track, so it's called a track if everything's at the same radius, because we have to be able to select some amount of information. So there'll be a track, which is the radius, and then a platter is which one you select, which it might also be called cylinder because it looks like a cylinder if it's 3D and we have multiple of these. And then within a track, there'll be different sectors, and then each of those will be of size, say a block or something like that. So there'll be a set size. So you'll be addressing things in sectors, which will be a set size, usually 4 kilobytes, and multiple sectors live on a track, and then there are multiple tracks across all the cylinders representing all the platters of the disk. So that's kind of what it looks like. And how it works too is that arm assembly can move back and forth, and then the disk can also rotate, so it rotates to spin all the disks, and that's what that loud sound is. So here, your access speed, because things physically have to move, really depends on how close two things are together. So if you have sectors on the same track, you can read them continuously, so you don't have to move the head at all. You're just reading the subsequent sector. So you essentially get it for free if it's already rotating anyways. So the magnetic head just goes and it can constantly read things, and it can actually do that fairly fast. But if your data is on another sector on a different track, well then the read-write head is going to have to move in and out, and it might be on the 180 side of the platter, so you're also going to have to wait for the disk to spin around and get to the sector that you want. So switching between tracks and repositioning that head is actually kind of slow, and repositioning the arm is also expensive. So when you are the kernel and you're writing things to access the hard drive, you have to say what sector you want. And you do that by addressing it in this old addressing mode called cylinder head sector. So you give each of those coordinates. So you can think of it as just, a coordinate where the platter is like the z-axis, so that's which head to write from. And then the track, or something historically the cylinder, is basically the radius, so what radii you want. And then the sector is just where in that track, which would be just like the degree. So this scheme has like an 8 gigabyte limit historically, because it assumes there are 512 bytes on a sector, and then up to 63 sectors a track, and then up to 255 heads. So that's how many tracks are in a cylinder, and then how many cylinders there are. So the alternative approach to just giving 3 coordinates to actually address a sector is something called logical block addressing. So it basically just uses an index to address any block. Yeah, just uses an index and then that goes straight to a sector. So it's not limited to 8 degrees, it's just however many indexes you have. So you can say however many index bits and that will just read you off a sector. But at that point, you have no idea about the actual geometry of the device. So you don't know if two sectors, even if they're, their indexes are right next to each other, they may actually be on different tracks because there has to be breaks somewhere. So you lose a bit of control if you want to like really, really optimize something if you use logical block addressing, because you're not guaranteed that any two sectors, if they're indexed, one apart, it doesn't mean they're right next to each other. So there's also this thing for hard drives called shingled magnetic recording, which is a kind of new thing that typically you want to avoid. Basically, the write head only writes in the center of the track and has some unused padding. So because there's magnetic interference and all that stuff. So under normal circumstances, when you have this, you can't write to the padding without destroying anything on the neighboring tracks. That's why there's padding. So there's some space where some interference can happen, and that's fine. It doesn't affect something on the next track. But with shingled magnetic recording, it basically takes advantage of this and writes over the padding if you do it in a certain way. So you have to guarantee all your writes happen at, like, say, outer tracks before inner tracks. And that way you can kind of overlap the interference a little bit and pack things even closer together. But you have to be really careful to do everything sequentially, or else that interference is still there and you might be able to ruin stuff. And also your performance may, if you don't know this is happening, your performance may suffer if you write in the opposite order than things are shingled, because then it's going to have to write all the data again just to modify a bit at the end, and you're going to have to do this over and over again. So it gives you some more density, but it also, if you use it incorrectly, your performance is going to suffer a lot. But it is cheaper, and if you buy cheap hard disks now, they might actually have this technology in them, and you actually have to check. So these hard disk drives, like I said, positioning the head and rotating the disk are not free, and the amount of time it takes just depends on the amount of physical distance it has to travel. So the rotational delay is the time it takes to physically rotate the disk to get to the correct sector, which would typically be like 4 to 8 milliseconds. If you assume the average delay is like half a full rotation, so yeah. So on average, it has to rotate half if you assume just completely random accesses. And then seek time is moving that head in and out to get to the correct track. Typically, this is a lot faster since it's on a track. It doesn't have to wait for anything to spin. It just moves up and down. So that would be like half a millisecond to 2 milliseconds. And then the transfer time is how long it takes to actually read bytes from the disk, assuming everything is sequential and in order, and we're just reading it as fast as we can from that magnetic head. And typically the maximum transfer speed for these kinds of disks are going to be somewhere in the neighborhood of like 125 megabytes a second, maybe 150, while our NVMe hard drives now are like 7,000 megabytes a second or something like that. So relatively slow, but still much, much cheaper. So if you were to calculate the transfer rate, well, it's some fairly simple math. The total time it takes to actually transfer some data, you have to take into account the rotational delay, so how long the disk takes to rotate, then how long it takes for that head to move in and out, and then how long it takes to actually read the data from that magnetic head and transfer it. So the transfer rate is going to be just equal to the size of the transfer divided by how long it takes, since that is the definition of transfer rate. And then we can answer the following questions like, hey, what is the transfer rate of large sequential accesses? And then what's the transfer rate of small random accesses for each disk? So you should use them sequentially whenever possible because your performance really, really badly degrades. So say we have two hard drives here. Hard drive 1 is like, a consumer one that you could buy off the shelf, and then hard drive 2 is more of like an enterprisey one. So you can see the enterprising one spins more than twice as fast, which is directly proportional to its rotational latency. So a consumer drive might be like 4.2 milliseconds, while an enterprise drive would be something like 2. And then the average seek time would also be about twice as fast on a more enterprisey drive, where the seek time for your consumer drive is like 9 milliseconds, enterprise would be like 4. And then the maximum transfer speed between the disks wouldn't actually be all that different. So like 105 megabytes a second versus 125 megabytes a second. They'd have the same number of platters, and their interface would be a bit different to actually communicate through the hardware. So for the sequential 100 megabyte read, we know our transfer rates because we're going to assume that this is the ideal case where the seek time is 0 and the rotational time is 0. So in that case, we're given our transfer rates. So if we want to calculate how long it takes for a 100 megabyte read, well, we have the rate, we have the amount of data we need to actually read, so we can calculate the time knowing that. Then the more interesting calculation comes when we actually want to calculate how long it takes for like a 4 kilobyte read. So you can see between the two hard drives, that's where the big difference comes in, even though they're both really, really slow. So if you just had to read like 4 kilobytes of data randomly, that could be anywhere on the disk, it would be something like 0.3 megabytes a second versus 0.6 for the enterprise drive. Yeah.
So is T the transfer time or the total?
The total time.
Which is just the transfer time. Is that like 0 or 0?
Yeah. So for the first one, where we calculate the transfer time for the sequential accesses, we're just assuming the seek and rotational time are 0. So if T is the total time, it only comes from the transfer time.
Okay, and you did 100 times.
Yeah, so for the first hard drive there, so for hard drive 1, oops. For hard drive 1, I'm just assuming that the rate is 105 megabytes a second. And then I know I'm transferring 100 megabytes. So, well, if that's the case, it's just 105 megabytes a second divided by 100. And then that would give us something like, the 850 milliseconds time, which would actually be like, 0.95 seconds. So that's that. The more interesting calculations for the 4 kilobyte read. So for the 4 kilobyte read, we can just go ahead and assume so we won't even bother. We'll just assume that we can read that 4 kilobytes instantly. So our total T is then going to be equal to average seek time plus average rotation, and then that's it. So we're just going to assume that the whole transfer time is instant. So for the first hard drive, for HDD1, well, the numbers on the slide was our average seek time was 4.2 milliseconds, and then our average rotation was 9 milliseconds. So our whole time is going to be whatever that is, 13.2 milliseconds, which is the same as 0.0132 seconds. So then, in this case, the amount of data we're transferring is 4 kilobytes, and then we can actually assume it's like the hard drive manufacturer run. So where 4 kilobytes is actually where 1 megabyte is actually 1,000 kilobytes, which is not really that true. So we know that, you know, if we do powers of 2, well, 1 kilobyte like this equals 2 to the 10 bytes. But hard drive manufacturers do not believe that. Hard drive manufacturers believe 1 kilobyte equals 1,000 bytes. And this is why if you've ever bought like a 1 terabyte hard drive and then you try to use it, it would only be like 900 and something gigabytes. Well, that's because hard drive manufacturers don't believe in powers of 2. They believe in 1,000. So they can sell you something that you think is bigger than it actually is. So because there's a difference of like 24 bytes, for it's like 1 kilobyte, the number will be like kind of similar. But if you get up to like 1 megabyte, well, hard drive manufacturers think that is, you know, 1 million bytes. Well, you probably believe it's like 2 to the 20. Which, what's 2 to the 20? Python, oh, cool. Yeah, so 2 to the 20 is like actually something like this. And then it's going to be even worse if you believe 1 gigabyte is like 1 billion bytes. And then you think it's 2 to the 30, then the numbers are going to be even more wildly different. So that is why you buy a 1 terabyte hard drive. It's not actually 1 terabyte. So that's marketing for you. So if we go ahead and do this, then, oops. Yeah, then we can calculate our rate. So our rate is just going to be d divided by t, so how much data we're transferring divided by how long it takes. And then this is 0.004 megabytes divided by 0.0132 seconds. So that gives us our 0.351 megabytes a second. So that was for hard drive 1. If we do the same thing for hard drive 2, well, we can just get the rate directly. So the rate, we're transferring the same amount of data. In this case, it's going to be way faster because we're going to add 2 plus 4, which is like going to be about more than twice as fast because it spins a lot faster. So that would be 6 milliseconds, which is 0.001 seconds. So that would be 0.66 megabytes a second. So that's the two differences between the drive, some fairly simple math. So when we have that logical mapping, remember that's like you just have an index that you can just index sectors, but you don't know where they are on the disk. If your hard drive, or if you're using a hard drive, you probably want them numbered like this, where most of them, if they're sequential in the order, are actually located next to each other in the same direction that the disk spins. So here, I could sequentially access, block 0 all the way to 11. And if I do that all in order, it would be all sequential and be really fast. And then I have a break between 11 and 12 where I have to move tracks. But I try and minimize that as much as possible. So then if you assume that, you actually don't have to use all those 3 coordinates, and you get pretty good performance without actually having to do any complicated looking into the hardware or anything like that. So yeah, and also too here, because it spins, you may want to optimize this a bit better. So when you transfer from, you're reading sector 11 and you have to move it to sector 12, so you have to move it between tracks. If you're designing the hardware, you would actually want to number that such that by the time the head moves to the next track, that sector 12 would be under the head and being able to read as quickly as possible. And then you don't have to, and then if you're the kernel and you're scheduling this, you just access them all in order, and then it's as fast as it could possibly be. So that actually makes it a bit more efficient. But you may want some more flexibility, so that's like really simple to program. You just try and access things in order. It tries to reduce the seek time for sequential accesses as much as possible. But if you are the kernel and you are controlling the file system, well, you can't try and inspect or try to optimize anything because you'll have no idea. Maybe you want to be absolutely sure that you don't change tracks or something like that. Well, with just this default mapping, you have no idea because you just have essentially one dimension in total. And you might be able to try and like reverse the mapping by seeing how your transfer rate is between different blocks, and then you can kind of figure out where the break is, but you might not want to do that. And also the hardware in a disk is quite complicated. So the number of sectors in a track might change, and also the disks, those sectors go bad randomly, and the disk will silently kind of remap them and say, hey, that sector is bad, I won't use it anymore, and then modify all the numbers, and then you'll quickly lose track of things because it won't stay consistent. And then this is where we get into our fun friend, a cache. So we've talked about all sorts of caches, so you can also use caches for disks to significantly speed up their transfers. So some disks will also have some internal memory. So like for the Western Digital Red ones, they have like 64 megabytes of cache. And what they can do is implement a read-ahead track buffer. So basically, it just reads the entire contents of a track while it's already there and keeps it in a cache. So if you're going to access some information that has already been read in that track, you don't have to wait for the disk to go around and spin back around to essentially where it started. It would just read from the cache because it's already passed by. And then other things you can do something called write caching with just your RAM. So if you modify any of these sectors, maybe you make like thousands of small changes to that file. Well, what the kernel can do is just keep essentially that block or sector in memory, so you can modify it. You just modify it as if it's memory, and it won't actually write that data back out to disk until you're finished with it or you actually tell it you want it. So there's some strategies you can use. You can either explicitly say, hey, write this back to disk, or you can kind of claim it's written back to disk. So if you want to be really, really fast, you can say, hey, kernel, please write this to disk. I've modified it. And then the kernel can say, yep, I did that, and then lie to you and not actually do it. And then it's going to look really, really fast, because if you keep on modifying that or reading that data, you'll see the modified data. But if there's power loss because it's essentially only in memory, and we know that if your memory is volatile, so if the power goes off, all your information is gone. So if there's power failure, you're actually going to lose data, and that's not going to be good. And then the other thing is, if you really are serious about things being written, you can do something called write through. So you actually get an acknowledgement that the data is physically written to disk, where you can guarantee that if there's a power failure, that data that's actually written, and you're not going to lose any data. So if you're like implementing file systems, you would actually probably want to be notified of that if you actually care about your data. Okay, and the fun thing about this too is we can schedule them. So scheduling is still a thing here. So you want to minimize the amount of time the disk moves without reading or writing data, and this mostly applies to if you actually have access to all three coordinates. So you can actually do first come, first serve, and if your programs are reading and writing to sectors, you can just schedule them in the order that they're received. Remember, your kernel is going to be way faster than the disk because disks are fairly slow. So if you do first come, first serve for essentially like sector accesses or block accesses, they'll be fair, but this is going to have, it's essentially going to be random accesses that you might be able to do better at. So the first thing we can look at is something called shortest seek time first. So in that scenario, if I have a bunch of requests, I'm going to service them in the order that they're the closest to wherever the hell my head currently is at. So I'm trying to reduce the amount of arm movement or seek time, but this is also going to be unfair because it's essentially like the hard disk version of shortest remaining time first. So I'm just going to only do the close accesses. So if there's an access that's really far away, it may get starved because all your other accesses are really close together, so it would actually service them instead. So what you can do is an algorithm called the elevator, which sweeps across the disks. So if a request, so say these are our requests for, sector 0, 12, and 20. Well, what the elevator does is it will essentially go sequentially through the tracks. So it'll go through this track, and then this track, and only service requests that are already kind of active at the time it goes through, and it won't go backwards. So it won't go backwards until it reaches all the way to the top, and then it'll go back. So in this case, it would start at the outside track, read sector 0, and then after that track's done, it would go read 12. Then after that track's done, it would read 20. So what it would do is if the elevator is currently moving up, so say we read 0 and then we moved up for 12, and then we had a request come in for like 1 or something like that, something on the outer track. Well, the elevator is moving up, so it wouldn't actually read sector 1 until the elevator goes back down to the floor and restarts again. So does that kind of make sense to everyone? Hopefully. So what that elevator does too is actually ignore rotation. So typically that shortest positioning time first is often the best strategy, but you need to work together to actually implement that. So elevator, because it ignores rotation, might actually not be the most efficient thing. So you might want to use a combination of that and the shortest positioning time first. So you try and minimize the amount of the distance between physical sectors so you don't have to rotate the disk or move the arm. Yeah.
So is elevator shortest positioning time first?
No, so elevator would work through the tracks in order, and it doesn't care about where they are rotationally. So say with this example too, so say instead of we had 0, 12, 20, and say we also had 6. So if those were all our requests, well, a faster thing to do might be to read 0, 12, 20 while it's moving up and then read 6 afterwards. But the elevator would do everything on the same track first. So if we also had a request for 6, it would read 0, 6, 12, 20, and then keep going up. And then say we read 0, then 6, and then move to 12. Well, if a request comes in for 5, then it's not going to do that until the next time it goes through. So
So it like scans horizontally.
yeah, so it goes horizontally. So it goes like, it would go outside track, all the requests for the outside track, move a track in, do all the requests there, move a track in, do all the requests there, and then reset the head back to the beginning. So with the elevator, the track only moves in one direction and then resets back to the bottom and then moves only in one direction.
So for 0, 12, 26, you said it would go 0, 12, 26 outward, right?
If we, yeah, so if we had 0, 12, 20, and then 6, if it's elevator, it would do everything on the outer ring first. So it would do 0, 6, 12, 20, while the fastest thing to do might be to go like 0, 12, 20, and then 6 afterwards and get all the other ones sequentially, because I'm going to have to, if I do 0, then 6, I have to 0, then spin this thing 180, and then read 6, and then I have to go spin it 180 again to get all the way back to 12. So instead I could have just went 0, 12, 20 without spinning, without having to wait for it at all, essentially if they were lined up, and then I just move the head while it's rotating 180 degrees and then pick off the 6. So that, yeah, so elevator's a bit slower, but it's going to be fair and not have that starvation issue. Because if I just did shortest positioning time first, say I just had requests, all next to each other here that kept on showing up again and again and again, and then I also had a request for 20, well, 20 might never actually get read, and it just stays on the outer track and just does all the lower requests. So, yeah, so you have the same idea with starving a process. You could starve a block on the disk. Okay, so disenable persistence. So we explored kind of 2 hard drives, like the enterprise one, the other, the enterprise one, the consumer one, saw, shingled, non-shingled, saw kind of 2 options for a whole bunch of hard drives. But basically, the magnetic disks have really poor random access. They also need scheduling, which, good thing we learned scheduling. And then if we do shortest positioning time first, that's kind of the best. I mean, that minimizes actually waiting for any mechanical thing to move. So that would be the best scheduling for throughput, but kind of like shortest remaining time first, it's going to maybe have issues with starvation. So our whole scheduling, it's still a trade-off even with this. Okay, now, do we have any final quiz 3 thoughts, concerns, or anything like that? Yeah.
It's kind of like what the structure is like, since the structure for the past 2 quizzes have been quite varied, because some of them have a lot of true false, and the second one had a lot more long answers.
Yeah, so this one's kind of between. So it has 1 scheduling multiple choice, which is like kind of short-ish, but not a short one. And then 10 quick multiple choices of virtual memory, and then a written one about scheduling, which would be like, hey, some benefits or drawbacks. And then page replacement, which would just be like a longer one of like, what's all the page faults at each time, and then a paging question. So given this virtual address, tell me what it is. So 3 longer-ish questions, and then otherwise multiple choice. So somewhere between quiz 1 and 2. So it's 40 points total, which isn't super ideal, but it's better than quiz 2, because that was only 30 and had only a few questions. Yep.
So since the final is kind of type A, so that means that no notes are going to be allowed, and is the format still going to be pretty similar to the previous?
For the final format?
Yeah.
I do not know what the final format is going to look like. So it's in a computer lab. I believe it's a Quarkus quiz, but it's a supervised Quarkus quiz. So
Quarkus is using internet, then like how are you gonna like make sure that students are not going to use like internet to take a look into like information?
so you'll be doing it in the computer labs. So you'll be supervised. And they're restricting, oh no, they're doing some setup where they're like restricting something or other. So they have a setup for the machines there, so you have to go on the machine and do it. Yeah. So that, yeah, it'll be an in-person online quiz. All right, well, I'll finish this up and then I'll answer questions, I guess, off stream. So just remember, pulling for you. We're on this